Bengali poetry, Professor Chatterjee will enlighten us today on the subject of soliton and soliton interactions in plasma. Please kindly join me to welcome Professor Chatterjee in this platform. Sir, over to you, sir.
ভিডিওটা কি আছে অন করে রাখছি ক্যান্সেল করে দিন শেয়ার করে হচ্ছে না তো ভিডিওটা হচ্ছে না আই দ্যাট টু আই তো কি যাইছো তুমি এই তো শেয়ার
Professor Chatterjee, you can continue.
আমি হচ্ছে না কেন এই তো উইন্ডো এই যে শেয়ার শেয়ার সব শুনতে পাচ্ছি মনে কথা এই দাদা শেয়ার করে Okay, am I audible?
Yes, sir, you are audible, sir. Kindly, can you make it full screen?
Is it whether hello, my can I whether screens are shared?
Your screen is shared, sir. So, could you please make it full screen?
So let me. Oh, okay. So now it is shared, na?
Yes, sir, it is shared.
So I'm audible. So good morning, everybody. Okay. First, I should like to thank the organizers because for inviting me to deliver my feeling about solitons and soliton interactions. Is my voice is okay or am I a little bit louder?
No, it's fine, sir. It's audible.
Yes, yeah, okay.
Sir, if possible, make your slide full screen.
Slides?
In full screen mode.
Is it okay?
Okay.
Is it
sir,
okay?
Continue. Yes, sir. Okay, continue.
So I am going to share my feeling about solitons and soliton interactions, especially in plasma. I just split my lectures in the following way: introduction, solitons, the history, how soliton research become important, how and why the soliton research become important in the scientific community. Then there are nonlinear equations, nonlinear differential equations, which arises in almost every branch of sciences. So to study soliton or solitary waves, KdV equation is one such equation. That is a nonlinear equation having some fantastic feature. So just I explain how a KdV equation is derived in plasma. That is how from a natural phenomena a differential equation is evolved. In last lecture, several times I have heard the students asking about modeling. Modeling means simple, that is from a complex physical or social phenomena, you have to construct some equations or construct some mathematical structure, simple structure that can be handled easily. So KdV differential equations are one such equations which model the physical systems. That's why differential equations are very important in almost all branches of sciences. KdV equation is one such equation which contain at the same time the nonlinearity and the dispersion. Because of the presence of nonlinearity and dispersion, the shape of a wave become same even in case of nonlinearity. And I'll explain in brief what will be the benefit of our civilization because of this development. Then I shall discuss something like soliton interaction, how these soliton interact. Either interact three soliton interactions, provided the solitons are moving in one direction, and head-on collision of solitons, provided the solitons are moving face to face and collide face to face in opposite direction and collide face to face. So first I say what is a soliton. Before telling solitary wave, let me say it's known to everybody why wave phenomena is that much important. You know, our universe is made of two things. One is matter, another is energy. So matter and energy combination makes our universe. So always some energy is needed to send any information. Like just I am talking now, and it is an the energy captured by the laptop and transported into this is the sound energy is converted into electromagnetic waves, that is electromagnetic energy. Then it is transmitted and captured by you also through your computer. So energy carries information. So important thing is that while we send some information through wave, then there may be a leakage. Why? Because wave have two type of velocities. One is called phase velocity, another is called group velocity. Phase velocity is the velocity of phase, that is related to space and time, change of space and time. But a single wave cannot carry information. Like those who know Guru, like Gurudev's song, they have heard that Aktaratir Aktitane Ganer Bedon Boitenare. The same thing, that is a single wave cannot carry information. Information can be carried only by a group of waves. So this group of wave have some particular velocity group, that is called group velocity, and energy moves with group velocity. The fantastic thing happened to solitary waves and soliton is that they move with group velocity. So solitary wave or soliton, they can move with the velocity of the energy. So nowadays we are getting energy, suppose electrical energy, either from thermal power plant or from hydel power project, and those energy is carried to several places where we are using the energy. But in the way, most of the energy is wasted. More than 70%, sometimes 60% energy is wasted because we could not carry those energy properly. If we can carry that energy in the form of a solitary waves or solitons, then all the waste will be gone. We can use 100% of the energy. That's why you have seen nowadays that fiber optics is used instead of the old aluminum wires. Because through fiber optics, the energy can come in the form of a nonlinear Schrodinger equation, another famous equation. So that's why study solitary waves and solitons are really important in the present world. Suppose in the computer, what we are using, this computer is basically have some electronic circuits, and the electronic circuits are made of some ICs, chips like that. So mathematically, the electronic circuit is not the computer. It is doing something for the computing. It's a replica of a mathematical concept. So even if possible, if we can create some hypothetical or optical switches, that is without using electronic gadget, just optical gadget can replace the ICs, then we can run computer. For that computer, we need no material, no matter, only some switch on some screen can do like a computer. So then the information in that computer should go in the form of a solitary wave or solitons. The research is still going on in this way, how electronic pulses can be worked as a soliton and can create an optical computer where no need for a material or electronic gadget for building a computer. So however it may be, those are the possible area of future research of solitons or solitary waves. I am just to make the user friendly or student friendly. I want to say some story. This is the man whose picture I am showing. Is John Scott Russell is a naval architect. He was a Scottish naval architect in 1834 while he was moving from London to Edinburgh by a boat, and the boat was carried by the horses. Then he watched that a heap of wave was moving in front of him without any dispersion. That is what we have seen always. It may be in the pond, it may be in the ocean. The one thing what we are observing, if any wave developed while it come to the shore, it diminishes. But what Scott Russell observed, that the wave is moving in front of him without changing its shape. He was amazed how it happened. So he chased the wave, and after few miles, he has seen that the wave kept intact its shape. Wave was behaved like a particle. He surprised. He just wrote his observation in the famous philosophical magazine, but people thought that Scott Russell was over enthusiastic about his observation. He may have seen He may have seen some big waves, large wave. He may chase a wave for 50 meters, but he wrote it's few kilometers because in common sense it was not possible. But this few people started thinking this, okay, whether it happens or not. This is observed long after Russell's observation, while in a laboratory people really created that type of wave. So when Russell reported in August 1834, so people didn't give much importance to Russell's observation. Later, in 1897, two famous mathematicians, Korteweg and De Vries, they have shown mathematically that it's possible to derive a nonlinear partial differential equation whose solution may come in such a way that the solution that the wave solution may come in such a way that the wave will neither just not dissipate from, but they balance each other such that the wave can move without changing its shape for a long time, mathematically for an infinite time. Why it happened? Because every nonlinear wave have at least one nonlinear term. The simplest nonlinear term may be written as u into del u del x type. If we integrate, it's a simple integration. U du dx, it will come u square by 2, that is energy. So if there is nonlinearity in the medium, because everywhere there is nonlinearity. Linearity is a phenomenon where generally we teach it in school, college, or university level. But in reality, everything is nonlinear. Almost everything is nonlinear. So the energy intake become more and more, and the wave will burst soon. In the other way, the natural waves, what we are observing in pond is that with the movement of the wave, it loses its energy, and ultimately when it enters the shore, all the shape is gone. This is because of dispersion. So when dispersion and nonlinearity balances exactly, that is the amount of dispersion done by a wave for a particular time, the same amount of nonlinearity, same amount of energy obtained through nonlinearity for that instant, then we can see that the wave can move without changing its shape and energy. Some drastic phenomena like tsunami may occur very near to the seashore while the energy is intact. After that, it was 1897. So it was a fantastic work. So it would have been developed soon. But what had happened that in 1905, Einstein published 5 papers, one in relativity, another in photoelectricity, mainly another in statistical mechanics. All these 3 papers developed new areas of physics, and almost all interested physics students entered their brain in those areas. Very soon, quantum mechanics developed, relativity and gravitation become one of the famous field, and statistical mechanics and Brownian motion will become another famous field. So for 50 years, like 1905 to 1955, it was basically Einstein, Bohr, and all sorts of particle physics and their development, gravity, particle physics, statistical mechanics. So they forgot the nonlinear science. Until in 1965, when these two famous mathematicians, Jabuski and Pascal, they have shown that even after collision, this wave can will not change their shape. They can intact their shape. That is, although they are waves, but they can be behave like particles. So earlier we used to call this wave as solitary wave. Now after the observation of Jabuski and Pascal, instead of solitary wave, we started talking this wave as solitons, like proton, like electron, like photon. We call the wave as soliton. Nowadays, other than soliton, several other waves are observed mathematically and physically. So very soon in 1960s, people started observing solitons in different areas. Like in applied mathematics, people started observing solitons in water waves, in optical fibers, in electronics, in several biological systems. In high energy physics, people started observing solitons in particle physics, plasma physics, gauge theory, string theory even. In pure mathematics also, special functions, algebraic geometry and group theory, the applications of solitons become very important. And because of this thing, nowadays the study of nonlinear sciences is increasing day by day. So several nonlinear partial differential equations arises. There are thousands of partial differential equations, nonlinear partial differential equations arises from from almost all physical branches. Like this is the Kotoik and Debris KdV equation, del u del t plus 6u del u del x plus del c u del x3 equal to 0. This del c u del x3 is the dispersion term. Due to this term, a wave dissipate. And if we remove u, then del u del t plus 6 del u del x, it is the linear wave which moves with a constant velocity. But in presence of u, make it complicated. So this is the nonlinear term. When this nonlinear and this person balances exactly, then we get the shape of a solitary wave. There are other equations also produces solitary waves. Like this is the nonlinear Schrodinger equation. It arises in fiber optics. This is the Sine-Gordon equation. This is the Kodom-Step-Petrius-Vili or KP equation. This is 2 plus 1 dimensional KdV equation. There are Zakharov equation. There are Barjat equations. Thousands of equations arises. And we started understanding the nonlinear feature and beauty of the nonlinear feature. Now I say something about plasma and solitons in plasma. Actually, plasma is called, in some sense, it is called fourth set of matter after solid, liquid, gas, and next is this plasma. If we heat and solid, the solid will become liquid because the crystal lattice structure between the molecules are break, and we get a new shape which is called a liquid. If liquid is heated and the mm, rate of evaporation is more than the rate of recondensation, then we get a new state which is called gaseous state. If the gas is heated much, then the electrons will leave the molecules and we get a new state which is called plasma. So globally in a plasma, number of positive charge and number of negative charge are same, but locally there are places where some changes is seen in the amount of positive and negative charge due to the due to the imbalance of positive and negative charge. Some disturbance occur in that area and wave occurs due to that region. You know, our civilization is running with shortage of energy because coal or what is the fuel oil are not infinite. So we need some other way. Getting energy from sun or from wind or from sea is not that easy. The simplest possible, if through which we can get simplest possible way, through which we can get infinite energy is through fusion research. The same way the hydrogen bomb or the atom bombs are made, if we can control the same system, then it is a field of plasma science. It is called tokamak research. So we are really serious how and in which way a tokamak may be developed so that the energy crisis of the present civilization will go. Here I have done some theoretical works. In my first part, just I have shown how a system is modeled, how from a physical system an equation is evolved. So naturally, for physics, you know, there are two very fundamental principles of physics. One is homogeneity of space and time, another is isotropy and space and time. Due to homogeneity and isotropy of space, equation of continuity, equation of momentum balance, and equation of state. Here we consider equation of continuity, equation of momentum balance, and Poisson equation. Equation of continuity is like same like fluid, that is the rate of change of hello. Okay, rate of change of density and rate of change of flux balances each other. So here density means number density. Similar to the momentum balance equation, it's like Newton's law. Du dt is converted into del u del t plus u del u del x. Du dt means suppose you are standing in front of a road and you are observing the change of crowd on the road. So del u del t means the change of crowd at particular time, and u del u del x means you are riding in the back of a motorbike and moving with the crowd and observing the change of the crowd with respect to space. So these two things are del u del t plus u del u del x. So this is du dt. According to Newton's law, this should be equal to F, force. If the force is the potential field of force, then generally a phi exists, and we can write the momentum balance equation in the form of 2. Poisson equation is a standard equation. The charge, the final charge is equal to del 2 phi del x2, when e to the power phi is the electron number density and n is the ion number density. These two number density will be calculated from 1 and 2, and let us see how we handle this problem. So generally this is a nonlinear differential equation. So nonlinear wave appear, but before observing nonlinear waves, we observe the linear waves. So my first task is to linearize this equation, and after linearization, we see what type of linear wave may arise in this wave. Then we guess that okay, if this type of linear wave arises in this system, then it may happen that some similar type of nonlinear wave may arise. So to do this, we consider this perturbation. Like initially, we consider that all the charges are balanced. That is when this phi equal to 0 and n equal to 1. So there is no charges, no charge separation. But suddenly there is a change with the positive charge. That is n become 1 plus n bar. So accordingly, the velocity started, velocity become u bar and phi become phi bar. This is small, n bar, u bar and phi bar. And if we replace n, u, and phi by these three equations, then naturally we get three set set of three linear equations. Now we again approximate that these perturbed quantities are proportional to e to the power I into kx minus omega t, that is they are wavy in nature. E to the power, e to the power I into kx minus omega t, according to Euler's formula, it is sine kx minus omega t plus sine and cos. So instead of writing sine and cos, we generally write in terms of e to the power I into kx minus omega t, because calculation will be simple in this particular case, where omega is the frequency and k is the wave vector. Now putting all these n bar, u bar, and phi bar in these three equations, we get three algebraic equations. These are the three algebraic equations which gives us relation between omega and k. This is a system of linear equation and homogeneous. The condition under which a system of homogeneous leads the solution of a system of linear, non-trivial solution of a homogeneous nonlinear system exists is that determinant should be equal to 0. Because if the determinant non-zero, so the condition under which we get non-trivial n0, u0, phi0 is the determinant equal to 0. Because naturally, if we put in n0 equal to 0, u0 equal to 0, phi0 equal to 0, equation satisfied. So we want some non-trivial solution. From this condition, we get the simple relation between omega and k, that is omega square equal to k square by 1 plus k square. This relation is called dispersion relation, because this relation will teach us how the wave disperses. So accordingly, if we expand omega in terms of k, we get omega equal to k minus k cube by 2, because k is small. So the phase velocity will be omega wave 1 by square root of k square plus 1, and group velocity will be 1 by k square plus 1 whole to the power 3 by 2. So what will be the phase? Kx minus omega 2 t is the phase. Phase will become k into x minus t plus half k cube into t. See, the time t is associated with k in two ways. Time t is associated with k simply, and time t is also associated with k in the form of k cube. So dynamically, k into x minus t and k cube into t have same dynamic status, and these two things simultaneously produces the desired wave what for we are looking. So x, if we write just k equal to epsilon to the power half, and we need, so naturally we need two different coordinates. One coordinate k into x minus t, another coordinate k cube into t. So let us write k into x minus t equal to xi and k cube into t equal to tau. So xi coordinate is nothing but some straight line along the characteristics of the partial differential equation, and tau is the time evolution provided the stretching is with epsilon to the power 3 by 2. So if k is small, this time is small, tau is smaller than the xi. Epsilon is called the strength of nonlinearity, and naturally we have taken a v arbitrary velocity which represent the Mach number of the wave, that wave through which it evolves. So here we consider a real model, same model, or the electrons of a particular kappa distribution. For this model, we want to find out the nonlinear evolution equation. We have taken the stress coordinates same as xi and tau, and we take the expansion as a and u phi like 9, 10, and 11. And we started calculating the terms of first order of epsilon and second order of epsilon. From first order of epsilon, we obtain equation 12. That is v square equal to 1 by a into 1 minus mu, where a equal to kappa minus half by kappa minus 3 by 2. This result give us the velocity or Mach number of the wave through which the velocity moves. And next order of epsilon gives us the famous KdV equation. It tells us that okay, in these circumstances, it is possible that the perturbed quantities can create a KdV equation through which we can find a soliton which moves with a particular velocity, which without changing its shape with a particular velocity. So now our aim is to see whether it has a single peak or double peak. If we integrate with this equation 13 in a simple way, taking a Galilean type transformation, we got a sec h square profile. But later people trying to understand that even in laboratory, we have seen several types of pulses appear like solitons. To do this, we have taken Hirota bilinear method. So we converted this equation 13 into equation 14 by this transformation. After taking this transformation, this is a standard KdV equation. And if we use this transformation, phi 1 equal to 2 del 2 del j 2 of ln f, and where f is considered in this complicated fashion, then we can find out A11, A12, A13, everything, and this theta, and ultimately we obtained the expression for phi 1. Phi 1 equal to 12 b to the power 1 3 by a into n by d. Equation 19 gives us the shape of multi-soliton. So this equation 20 gives us the final expression for multi-soliton. There is a huge calculation. I am not going to just show you in the detail. Rather, I want to tell you some fantastic thing. Like from this calculation, if we do some more manipulation, we can see that the 1, 2, or 3 soliton pulses appear. That is all. Although the calculation looks like very complicated, but after simplification, we can see that that complicated equation gives us 3 simple equations with some delta I. This delta I equal to given by this. Its physical means that even when 3 or 4 or more than 4, when n type of solitons appear, after collision, the soliton will interact same, but there is a change of phase only, little bit change of phase only. So people have studied several problems using this soliton interaction, but the question here is that mathematically it is proved that the solitons preserve their shape after collision, even after infinite time. But what will happen at the time of interaction? We should see, we should concentrate on the time when the interaction is happening, or at the neighborhood of the time when interaction is happening. What happens to the energy of the solitary waves when interaction is happening? So this is the first work basically in plasma field. That is, our group have shown that while soliton interact, they create turbulence in the medium. They create turbulence in the medium. Turbulence is the one of the uh, most interesting phenomena which have not yet been understood clearly. So this may help the laboratory people to understand plasma experiment or tokamak research better ways. How have we done it? First, we have observed the peaks, how after collision, whether the wave will get a single peak or not, whether they will get double peak or not. It is done by simple calculation, and we have found out the restrictions under which some single peak are that or not. Suppose these 3 waves are moving in this direction. So this is the tall man. The tall man, while running, tall man can beat the short peoples. So here the tall man start, all these 3 waves started moving in this direction. So ultimately they came to a single peak, and ultimately the tall man move forward. So from this point to this point, the solitons regain their shape. There is no problem with these 2 areas when t equal to suppose minus 60 to t equal to plus 60. But what will happen in this region where the interaction is going on? Whether the soliton, whether the region will be same or something happened to that region. We have shown that no, some disturbance in terms of turbulence, it is called wave turbulence, and weak wave turbulence, that is soliton turbulence, occur in the medium. So how we have observed? Here also we have shown that it's not always that single peak occur. Sometimes a double peak or triple peak occur, but this is final, that is tall wave just beats the shorter wave in its journey, and ultimately the by disturbing the region with this time when the interaction is going on. This is another picture by which it is shown that different types of interaction happens in the region. So now we want to study the statistical properties, and we want to see how the turbulence occur in this situation. So actually, why KDB equation is so, KDB type equations are so stable? Why mathematically they are stable? Physically we can see that, okay, if nonlinearity and dispersion balances each other, but from mathematical point of view, we can say that KDB type equations follow infinite type of conservation principle. Because of this conservation principle, they are not like they are similar to that of mass conservation, momentum conservation, energy conservation. Because of all these conservation, KDB equations are very stable. I mean, even after interaction, they behave like particle. So just we have seen that is it happening for a multi-soliton even in the time of collision. To do this, we have calculated these four conserved quantities, and we have seen that they are constants. But to understand the effect of C-soliton interaction on the statistical moment of the random wave field, the following integrals are also considered. These are moments, these are statistical wave field like mean, median, mode, standard deviation, skewness, kurtosis, etc., etc. These are very important to study any statistical wave field. And we have seen that the skewness and kurtosis, these two parameters plays an important role to finding the disturbance of the medium, creating the medium little bit turbulent. Where I1 and I2, these are constant, but M3 and M4, these are M3 and M4 for separate. The evolution of skewness and kurtosis is so in figure 6. The solitons do not interact. If the soliton do not interact, the skewness and kurtosis are constant, but if they interact, then it is seen that skewness and kurtosis changes in this particular region, almost minus 60 to plus 60. So what we have seen in the figure, that in the time of interaction, really the skewness and kurtosis are not constant. So the medium is disturbed. According to Kolmogorov, this is the little bit slow turbulence occur in plasma. In case of in a plasma model, if the three solitons are moving in a particular direction, just there are another type of collision may occur in a plasma. If the these are called head-on collision. If two or more solitons just move in a line to each other and interact face to face, then we see what will happen. So the technique is same, but here the perturbation technique is a bit different. It is called PLK technique or Poincare QO likelihood technique. By this technique, we can obtain two KDB equation written by equation 48 and 49. Because of this sign here, positive and negative, it can be shown that they move each other and they interact. So like previous way, this is the dispersion relation. This is the simple soliton solution. These are the phase shifts given by equation 53, 54. This by the same way, Hirata's bilinear method, we obtain the multi-soliton solution. This is F1 for the first wave, first KDB equation, and F2 for the second KDB equation. These are the phase changes. So now you want to study that if analytically we can see that okay, even after a sufficient time, the shape will remain intact. But question arises that what will happen when there is an interaction. So same way we have studied the conjugate principle of the KdV equation. We have also studied the four conjugate quantities of KdV equation 49. These are the classical integrals we have observed. And here it is the picture of the head-on collision. Like these are the two wave, this wave moving in this way and this wave moving in this way. Ultimately they converge to the same equation, but ultimately this wave move to this portion, this wave move to this portion after collision. Sometimes they emerge to a single pulse, sometimes they may not emerge to a single pulse. So now to study the wave field, this is our main interest. We have also considered M1, M2, M3, M4. And M1 is mean, M2 is variance, M3 is skewness, and M4 is kurtosis. If there is no interaction, they are constant. But if there is interaction, then during the interaction, the three quantities, not only the skewness and kurtosis, but the variance, skewness, and kurtosis, all three properties of the wake field is changed in the time of interaction. So it is seen that while head-on collision, that is much stronger than the overtaking collision, because in overtaking collisions only skewness and kurtosis is changed in the region of interaction, but while head-on collision, along with the skewness and kurtosis, variance is also changed. So it's a very important and very interesting phenomena. These two phenomena are observed in plasma dynamics, in the field of plasma dynamics, first by our group. And this phenomena helps all the people, those who are doing experiment and those who want to find out tokamak. They have to careful at the region of interactions of solitons inside the tokamak or inside any plasma model, so that they can handle the turbulence. They can handle the turbulence. So this knowledge, I think, not today, but after 10 years or 20 years, will be very popular among the plasma physicists when the little bit development will occur in the field of tokamak. I thank everybody for allowing me to share my lecture. I am actually a bit busy now, so I could not uh, much time to illustrate the pictures in a better way. Whatever I have done, it's my way. Thank you. Thank you for listening me. If there are any queries or questions, I shall try to answer those things as far as my knowledge goes.
Thank you very much, sir, for your nice talk. I must say the initial session or initial part of your presentation was just like a storytelling session. So nicely you explained the history behind the soliton, starting from the name, how then it was named soliton. So I must say everybody will agree with me who is not in this subject, they also could sense the flavor of the subject because of your presentation only. So nicely you presented. So as now is the question and answer session. So anybody have any question? Directly you can unmute and ask the question to sir. Anyone is having any question?
I have one small question.
Yes.
That,
Kindly introduce yourself and then ask. Oh,
Okay, I know him.
it's Mondal sir.
He's my
Okay.
student.
Sorry, Mondal sir. I thought
Okay.
any other participant.
Okay,
Okay.
okay. Let's suppose I'll happy to listen your query.
can we use this model into the nanofluid? Can we clap this thing into the nanofluid model, plasma model, whichever
এই
you have
শুনতে পাচ্ছি
discussed?
না, একটু জোরে বলবি?
Sir, can we club these two model, means this KDB model or the soliton model with nanofluid model?
Yeah, actually in every area in nonlinear sciences, if you can handle properly, systematically, the nonlinear differential equation will appear. Clear? If there are equations like equation of continuity, equation of motion, and some other equation, Laplace or Poisson equation, whatever, Poisson is not necessary. So from that physics, if you model properly, the solitary wave or soliton will come, because this is the only mathematical model through which energy moves from one place to another. Clear? It may be in fluid dynamics, water waves, because it is done, huge work is done in water waves, huge work is done in nonlinear optics also. But there are areas still to explore how the energy moves from one place to another through nonlinear waves. It may happen that KDB equation will not come. Some new nonlinear equation may appear, because we don't know that what equation will come. Suppose if you consider magnetic field. So naturally, if we consider 2 plus 1 dimensional, then the different types of 2 plus 1 dimensional equations like Kodom-Step-Petrius-Will equation, Chakarov-Kuznetsov equation. Again, these equations may come with some damping term if we consider some collision. So due to collision, some damping term will appear. If some there are some way that some additional force may injected in some places, so the forcing term will come. So that forcing term may be in terms of periodic, maybe in terms of chaotic. So model can be done, it's sure, but solution will depend upon the complexity of the model. How far solution we can find out.
Okay, sir. Thank you very much, sir. Thank you for your nice explanation.
Thank you for your. But it's a
madam.
very interesting thing you asked.
Thank you very much, sir. Is there any more question? Okay. So if anyone have any question in future, you can mail to sir directly, and he will answer the question. So once again, thank you very much, sir, for your nice presentation. So we
Okay.
can have.
Thank you, everybody, from
Thank you.
my side, from the side of Vishwabharati, land of Tagore. Thank you.
Thank you, sir.
I'm somewhere, so I'm leaving you with your prior permission. Thank you.
Okay, sir. Okay, sir.
Yes, sir, you can do. Okay, so our next session, next keynote speaker is Professor Shankar Kumar Roy. So let me give a brief introduction to Professor Shankar Kumar Roy. Shankar Kumar Roy obtained his MSc in Applied Mathematics in 1996 from Vidyasagar University and PhD in 2003 from the Department of Mathematics, IIT Kharagpur, India. Currently, he is serving as a professor in the Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University, Midnapur. He delivered more than 30 invited lectures in India and abroad countries such as Spain, China, Indonesia, Germany, etc. His research interests are mainly in transportation problem, game theory, inventory management, and facility location problem, and biomathematics. He has published more than 120 articles in the area of operation research. 13 PhD students have been awarded under his supervision already, and many more students are pursuing PhD under his guidance. He is the life member of Calcutta Mathematical Society, Operation Research Society of India, International Society for Development and Sustainability, Japan, and senior member of IEDRC, Hong Kong. He has been selected as top 2% of scientists in the world in all disciplines during a single calendar year 2019 and 2020 also, based on the Stanford University study. He ranked 14th and 8th respectively in World Scientist and University ranking in the year 2020 and 2021. The title of the topic he is going to elaborate in this session is Towards Digitization of Uncertain Supply Chain, Management through Industry 4.0 and Fuzzy Logic. So I would like to welcome Professor Shankar Kumar Roy in this platform. So over to you, sir.
Am I audible to you?
Yes, you are audible. Okay. Yes, sir, you are audible.
Okay. So thank you very much for the nice introduction about me. First of all, I would like to thank Professor Surajit Chakrabarty, HOD of the Department of Mathematics, MIT Institute of Applied Sciences. And also thanks to all inter-community of this member of the conference. And I would like to thank the